Hey guys, this is Cambridge IGCSE Physics February-March 2020 paper 62. Question 1. A student is determining the density of wood by two methods. He is using the wooden rod shown in figure 1.1. We have a loop of thread around the wooden rod, and these are the length and diameter. Method 1. The dimensions of the wooden rod are shown full size in figure 1.2. Measure the length L and the diameter D of the wooden rod in figure 1.2. For length, you just have to measure this length, and for diameter, you'll have to measure this length across the center of the circle. They should be 4.5 cm and 2.0 cm. Make sure you put both of them to one decimal place because you're using a ruler, and a ruler can measure up to one decimal place. Suggest an accurate method for measuring the diameter of the wooden rod in this experiment. List any additional apparatus that might be required, and briefly describe how you determine the diameter. You may draw a diagram if it helps you to explain your answer. So instead of just measuring the diameter straight away with a ruler like this, there can be other methods. Well, as long as your answer makes sense, it's fine, but there are 4 examples given here, and it's always good to keep their methods in mind. So first of all, what you can do is, as it's shown in the diagram, you can put a loop of thread around the rod like this. Well, there should be a reason why they show that the thread can be around it. And when you put it around, don't just put it one turn, but put several turns around it, and you calculate the circumference of it. The circumference is basically this length, and you know that circumference equals to 2 pi r. And 2r is basically just the diameter, so from that you can calculate the diameter. Next, we can place the rod between 2 blocks like this. Then you measure the gap between the blocks. Then we have a simpler method, which is by just measuring the diameter across at several places. So in the beginning, we just measured here once, but we can start measuring this, these, and so on, and take the average. Then lastly, you can just use a micrometer or a vernier caliper, also at various points, and take the average. Part B. The student uses a balance to measure the mass m of the wooden rod as shown in figure 1.3. Record the mass m of the rod, it's just given here, 7.8 grams. Calculate the value rho 1 for the density of the wooden rod. Use your values from part A1 and B and the equation rho 1 equals to 4m over pi d square L. Include a suitable unit. So the values in part A1 was the length and the diameter, which were 4.5 and 2.0 cm. Then B is just the mass, 7.8 grams. Just substitute the values. 4 times 7.8 over pi times 2 squared times 4.5. Well, if you calculate that, we'll get 0.55, correct to 2 significant figures. And make sure you either use 2 significant figures or 3 significant figures. Doesn't matter which, but just try to keep it consistent. Okay, and since we used grams, it should be grams, and for these, they were in centimeters, and there are 2 values for diameter and 1 for length. In total, there are 3, so it's centimeter cubed. Method 2, Part C. The student pours water into a measuring cylinder as shown in figure 1.4. He then floats the wooden rod in the water as shown in figure 1.5. Record the reading V1 of the water level in the measuring cylinder as shown in figure 1.4. V1, it's over here. Make sure you read the bottom of the meniscus right over here. It's 144. Record the new reading V2 of the water level in the measuring cylinder with the rod floating in the water as shown in figure 1.5. Again, the bottom of the meniscus, it's 152. Part D. The student removes the rod and lowers a piece of modeling clay into the water as shown in figure 1.6. He then hooks the rod to the modeling clay and lowers them into the water as shown in figure 1.7. Now we have a clay, and above that you put the road. He records the new reading V3 of the water level in the measuring cylinder with the modeling clay. He records the reading V4 of the water level in the measuring cylinder with the modeling clay and road. They became 164 and 178. Calculate another value, row 2, for the density of the wooden road. Use the values from part C and D and the equation row 2 equals these, where k equals to 1. Easy, just substitute the values. Now V2 was 152 and V1 144, so 152 minus 144 over 178 minus 164 equals to 0.57. Now remember, we used two significant figures when we were calculating row 1. So again, we are rounding it up to 2SF. When I didn't put K here, but it's just 1, it doesn't make any difference, so I just left it out. Part E. On figure 1.8, draw an arrow showing the correct line of sight for reading the volume of water in the measuring cylinder. To avoid the parallax error, you should read it perpendicular to the measuring cylinder, so you just need to draw a straight arrow. Part F. Suggest a possible source of inaccuracy in method 2 even if it was carried out carefully. First of all, you're using measuring cylinders, and measuring cylinders are not really accurate. So you got your 1 mark, they are not accurate enough, and you're going to keep moving the clay and the road in and out of the measuring cylinder, and there can be water lost in the process, like the clay can absorb the water or the wood can absorb the water. Question 2. Students are investigating the cooling of hot water in a beaker. They're using the apparatus shown in figure 2.1. We're given with a beaker, thermometer, and the bench holding the thermometer. Record room temperature theta R shown on the thermometer in figure 2.1. It's 21 degrees Celsius. A volume of 150 cm³ of hot water is poured into the beaker, and the initial temperature theta is recorded in table 2.1. The temperature of the water is recorded every 30 seconds. The values are shown in table 2.1. So it's a simple experiment. You just put water and measure the temperature every 30 seconds. Complete the headings in table 2.1. Okay, the headings they're talking about is over here. This question can be easily left out, so be careful to complete all the questions. Well, the units are missing, so S and degree Celsius. Describe one precaution that you take to ensure that the temperature readings in the experiment are as accurate as possible. How to take accurate temperatures. First of all, again, avoid the parallax error by making sure that your line of sight is perpendicular to the scale. Then you can say you can stir before reading the scale because the temperature top of the beaker can be different from the temperature at the bottom of the beaker. Part C. Calculate the average cooling rate x1 during the first 90 seconds of the experiment. Use the readings from table 2.1 and this equation, where t equals to 90 seconds and theta 0 and theta 90 are the temperatures at t0 and t 90 seconds. Include the unit for the cooling rate. So what's the temperature at 0 seconds and 90 seconds? They are 95 and 79. So 95 minus 79 divided by 90 equals to 0.18. Calculate the average cooling rate x2 during the middle 90 seconds of the experiment. Use the readings from table 2.1 and the equation. Right, they're just giving us everything, just substitute the values. Now temperature at 90 degrees, it was 79, and at 180 degrees, it was 68.5. 79 minus 68.5 divided by 90, you should get 0.12 rounded to 2SF. Now we should add units here because this is the temperature and this is time represented by t equals to 90 seconds. So we add a unit here. Calculate the average cooling rate x3 during the last 90 seconds of the experiment. The same thing. Temperature when it was 180 seconds, it's 68.5. We just found it out. And for 270 seconds, it's 62.5. 0.07. Part D. The temperature of the water falls as time passes. Use the results from Part C to describe the pattern of the rate of cooling of the water during the experiment. Justify your answer by reference to your results. Now, what we've just calculated, x1, x2, and x3, these are the cooling rates, basically showing us how fast it cools down over a period of time. And you can see that overall, they are decreasing. So as time passes, the cooling rate decreases, and we need to justify this by stating our values of x1, x2, and x3. It's because x1 was 0.18, then x2 0.12, then x3 0.07. Give an estimate of the probable final temperature theta F of the water if left to cool for many hours. No matter how much you heat up the water, if you leave it to cool for many hours, it's just gonna reach its initial temperature. So we write its initial temperature, which was this, the room temperature, theta R. Part E. A student in another school carries out a similar experiment. She starts with the hot water at a lower initial temperature. Suggest how our cooling rates are likely to compare with those calculated in Part C. Use the results to explain your answer. If it starts at lower initial temperature, well, we can find out what will happen by going back to our table again. So this experiment started at 95 degrees, but let's say this person starts their experiment at 66 degrees. And the difference between this is that if you start at higher temperature, the rate of decreasing the temperature is much faster, so the cooling rates will be higher over here. However, if you start at lower temperature, you can see that the cooling rate is lower. It only decreased by a few degrees Celsius. So our suggestion is that there will be smaller cooling rates. And also we can explain using our results. For x1, when the initial temperature was high, the cooling rate was 0.18 degrees Celsius per second. But as the initial temperature decreased, at x3, it decreased to 0.07 degrees Celsius per second. So we're going to state these two values and say that the cooling rate is lower at lower temperatures. State one variable other than the initial temperature which the student should control. If it needs to be controlled, it means that it should be kept constant. So the most obvious one is the volume of water should be kept constant, because if you have higher volume of water, it's not going to decrease its temperature as quickly as a beaker with lower volume of water. And also, the room temperature where the student carries out the experiment should be the same, because let's say you're carrying it out at lower room temperature, then obviously the temperature will decrease faster. Question 3. A student is investigating a power supply. She's using the circuit shown in figure 3.1. This is a typical circuit shown in 2020 papers. We have the voltmeter, ammeter, and the crocodile clip, which can vary the length of the resistance wire. And this is important because the resistance is affected by the length and the diameter of the wire. Part A. The student connects the crocodile clip to a length 100 cm of the resistance wire and measures the potential difference V0 across terminals P and Q and the current I0 in the circuit. Record the values of V0 and I0 shown on the meters in figure 3.2 and 3.3. The voltage is here, it's 2.1. Then for the ammeter, it's somewhere in the middle of 0.2 and 0.3. That should be 0.26. Calculate the resistance R0 of 100 cm of the wire. Use your values of V0 and I0 and the equation R0 equals to V0 over I0. Simple, just add in the numbers 2.1 divided by 0.26. If you round this to 2SF, it will be 8.1. And yeah, I guess I'll just keep on using 2SF because these two were 2SF. Part B. The student that connects the crocodile clip to lengths 70 cm, 60 cm, 50 cm, 40 cm, and 30 cm of the resistance wire. She measures the current I in the circuit for each length. Her readings are shown in table 3.1. We have a column for the length, the current, and the inverse of the current. Calculate and record in table 3.1 the value of 1 over I for length 70 cm of the wire. Okay, it's obvious what we need to do. 1 divided by this number, 1 over 0.35 equals 2.86. Now plot a graph of L against 1 over I. You do not need to start your axis at the origin. Alright, they've told us which value goes to which axis, and yes, we do not need to start at the origin, so you can have your own scale. So let's see which scale would be the most appropriate for us. First, plot the axis. Alright, so for y-axis, we have 1, 2, 3, 4, 5 big boxes or big squares. And for length, they're from 30 to 70. So I guess you can just put these numbers, meaning we start from 30, 40, 50, 60, 70, and 80. Then for x-axis, we have 1, 2, 3, 4, 5, 6, 7 and half big squares. The range is from 1.54 to 2.86. So if you do some calculations, you can figure out that it can actually start from 1.4, then go on to 1.6, 1.8, so increasing by 0.2 every time. And at 2.8, but we have this half a box here. We'll be able to squeeze in until 2.9. Our answer is until 2.86, so this is fine. And now we can just plot the points. Okay, and my plots are definitely occupying more than half of the grid given, so they're fine. So now just connect these plots with a line of best fit. Part D. Determine the gradient g of the graph. Show clearly on the graph how you obtain the necessary information. Well, to find the gradient, we usually use this y2 minus y1 divided by x2 minus x1. While for physics, if they ask you to find the gradient in paper 6, we need to use something called the triangle method. It's actually the same thing, but you just need to draw the triangle on the graph to show which coordinates you have chosen. Well, for me, I'll be choosing these 2 points. Okay, after choosing your points, just draw a triangle. Okay, then find the difference between the y coordinates and divide it with the difference between the x coordinates. I got exactly 30 as my answer, and this depends on your graph and your calculations. Calculate the electromotive force EMF E of the power supply. Use your value of R0 from A2 and the equation E equals to G times R0 divided by K, where K equals to 100 cm. We have just found G, and R0 was here. It was 8.1. And K is 100, so if we calculate this, it's 30 times 8.1 divided by 100, and I got 2.4. Well, of course, this is also going to depend on your answer for part D1, G. They've given you the range in the mark scheme, so it should be in the range 2.0 to 2.9 volts. Well, the range is kind of big, so you should be able to get it. And as long as you've drawn the correct graph and calculated the gradient correctly, you'll be able to get the correct answer. Part D. The ammeter in this circuit has a small resistance which affects the current. The effect of the resistance on the measured current I will be different for each measured length L of the resistance wire. State and explain which length L will be most affected by the resistance of the ammeter. Okay, what they're saying is the ammeter in the circuit, this guy has very little resistance and it hardly affects the current. And they also mentioned that the current will be affected by the length of the resistance wire. And then they asked which length will be most affected by the resistance of the ammeter. So it's kind of confusing, like they first talk about the ammeter and then the length, the current, and then suddenly the length and the ammeter again. But you just need to know that ammeter has a small resistance but still has some resistance in the circuit, and current is dependent on the length. Considering the length of the wire, we had length from 30 cm to 70 cm, and we have to decide which length is gonna make the ammeter affect its resistance. Well, the answer is the shortest length, which is 30 cm, because if the length of the resistance wire is small, let's say like this guy is going to have very low resistance. And if the resistance of the resistance wire is low, the resistance of the ammeter, although it stays constant, will be taking a bigger part of the total resistance. Which brings us to a point that the resistance of the ammeter, although small, will still have a bigger effect on the resistance wire. Well, let's say you have a 70 cm resistance wire, so it should be like this. Then the resistance of this wire will be very high, and the resistance of the ammeter this time will be too small compared to the resistance of the 70 cm wire, so it won't be really considered as a big thing, and it won't be able to affect the resistance or the current in the resistance wire. Therefore, the answer is 30 cm. Reason because the ammeter will be forming a greater proportion of total resistance if the length of the resistance wire is shorter. Question 4. A student investigates a wind turbine, which is an electrical generator driven by a propeller blade. Plan an experiment which will enable him to investigate how the current in a resistor connected across the terminals of the turbine varies with the speed of the airflow through the turbine. The apparatus available includes a model wind turbine as shown in figure 4.1, this one, an electric fan to provide the moving air to turn the turbine. The fan is here, so there will be wind blowing here, which will turn the propeller blade, and a device for measuring airspeed. In your plan, you should list any additional apparatus needed, complete the wind turbine circuit diagram, state the key variables to be kept constant, explain briefly how to carry out the experiment, including how the speed of the airflow is to be changed. Explain how to use the readings to reach a conclusion. Alright, this time question 4 is not that easy, maybe because questions 1 to 3 was not that hard, but we can just follow the steps, but not just only follow the steps, because you know that this is a 7-mark question, but they've only given you 5 points, and you have to figure out the other points. Well, let me explain how the experiment will go. Basically, you're just gonna vary the speed of the electric fan, as stated here, and we need to measure the current generated from the propeller blade during that airspeed. So it's simple, you just turn on the fan but with different speeds and measure the current. Let's first complete the diagram. If you want to measure the current, obviously you'll need an ammeter. So all you need to do is actually just add an ammeter and close the circuit. One is done, and let's list the additional apparatus needed. As I have just drawn, we need an ammeter. And how are we gonna change the airspeed? Let's change it by varying the distance between the propeller blade and the electric fan. The airspeed will be higher if the fan was here and slower if it was here. So all we need to do is just vary the distance, and to measure the distance, we will need a meter rule. Then the key variables to be kept constant. Since we're just varying the distance between the propeller blade and the electric fan, the speed of this electric fan should be the same. So you cannot have lower speed and higher speed at the back here. The speed should be constant. Or you can say the height of this fan should be kept constant, because if it's smaller like this, it's gonna blow like this, and you'll definitely have different results. Now we have to explain the method and how the speed of the airflow is going to be changed. So first, place the electric fan maybe 10 cm away from the propeller blade, then measure the current from the ammeter, and then next 20 cm away, then next 30 cm away, 40 cm away, and so on. So you repeat for different values of distance between the propeller blade and the electric fan and measure the current every time. Okay, then explain how to use the readings to reach a conclusion. This is the analysis part, and we don't need to talk about the conclusion like which distance brings the bigger current and all that. We just need to state how we're going to use the readings to reach a conclusion. So usually you either draw a table or a graph. So let's say you want to draw a table. Then you can say you compare the readings to see if the change in the distance between the propeller blade and the electric fan produces change in current. You can do that with a table. You don't need to draw a table, just write, compare readings in the table, and so on. And if you want to plot a line graph, you can also say plot a line graph, but this time you have to mention which value goes to which axis. So for this, for x-axis, it should be the independent variable, so the distance will be in x-axis and the current will be in y-axis. Okay, I know we're done with the points that are given, but we need at least one extra point because the points are allocated like this. There is a famous point that is always included in most of the mark scheme, which is repeat each measurement and take the average. So make sure you always put in the point, and you can mention one other variable that needs to be kept constant, which is carry out the experiment where there is no wind inside a still room, so that the wind in the environment or in the surroundings does not affect the propeller blade and the current produced by it. That's it for this video. If you think this video helped you, please like and leave a comment. I really appreciate those. Subscribe to get ready for your IGCSE exams. Stay safe and God bless you guys. Bye!